Alright, this is a video on multiplying special cases of binomials. Alright, so we'll look at two specific types of unique cases where we get special outcomes. And we'll do an introduction, mostly a few examples in this video. The first example that we'll be doing is looking at perfect squares. So the example I have for you is the quantity x plus 5 squared. And I just want to show you the most common math mistake in all of high school is to think that this is equal to x squared plus 5 squared or x squared plus 25. So that's incorrect, okay? It's fine to make that mistake once or twice, but you definitely want to learn from it and move on and make sure you are getting correct results here. So I have a visual to show you what this would be using our algebra tiles. So here we have x right here, and then 1, 2, 3, 4, 5, okay? And we have the same thing over here. So this square is x plus 5 on each side, so its area should be x plus 5 quantity squared. And this will be an x squared, and each of these rectangles are going to be 1 by x. So it looks like we have 10 of them. And then each of these little squares in here, I'm not going to check them all off, but each of those guys are going to be 1 by 1, so they'll have a total area of 25. Okay, so x plus 5 quantity squared, the true outcome is x squared plus 10x plus 25. Okay, that's the correct outcome. Now you might be thinking, how can you do this without needing to draw out all those squares and rectangles each time? Well, just like in a prior video, we are going to be using the FOIL method. Remember, whenever we square something, it just means multiplying by itself. Okay, so we are going to get x squared. The outers are 5x. The inners are also 5x. And the lasts are 25. So that's how we get x squared plus 10x plus 25. But one of the points of this video is to show you some shortcuts. Okay, so if we do have a perfect square, I hope you can see that this 5 up here gets doubled to be a 10 and squared to be a 25. So that's the quick shortcut here. If we have a perfect square, a binomial that's being squared, this is going to be doubled and this is going to be squared relative to the 5 that's in the binomial. That rule falls apart if we have a coefficient in front of the x. So if we have something like 2x plus 5 squared, we'll still get a 25, but the 10x will turn into something different. Okay, but just for basic squaring of binomials, the middle term is doubled and the last term is squared. Foiling always works though, okay? So if you don't remember those shortcuts, you can always FOIL. Okay, the next example I want to look at is going to result in what we call a difference of two squares. And so I'm going to approach that with a little bit of a pattern, a little bit of an investigation. So I encourage you to pause the video here and try these on your own. They're pretty accessible, pretty doable. But we'll go ahead and go through them together. So let's see here. I'll draw some lines to sort of divvy up what we're doing. Okay. So 7 squared versus 8 times 6. Okay, 7 squared I hope we know is 49, and 8 times 6 is 48. Okay, how are those two related to each other? 4 squared is 16. 5 times 3 is 15. Do you see a similar pattern? It looks like if we subtract 1, we get the next one. We subtract 1, we get that next number. So 10 squared is 100. I'm going to predict that this one should be a 99, and it is. 11 times 9 is 99. Okay. So look at these patterns that we just developed, right? So the perfect square, we subtract 1 to get another product. But where did those products come from? 8 is 7 plus 1, and 6 is 7 minus 1. Looking at this 7. Okay, so let's go with the 4. 4 plus 1 is 5, 4 minus 1 is 3. Look at this 10. 10 plus 1 is 11, 10 minus 1 is 9. So same deal with x. X plus 1 and x minus 1. Okay, so this is x squared, and I'm going to predict that this outcome right here in yellow is going to be an x squared minus 1. Okay, and let's actually do the foiling to check it out. So we can do firsts, so we get x squared, outers we get minus 1x, inners we get plus 1x, and lasts we get minus 1. And then these two guys cancel out, the minus 1x plus 1x. So we do end up getting the x squared minus 1. So that's called a difference of two squares, because x squared is a square, and difference because we're subtracting, and then the 1 is a perfect square as well. Okay, so that's a little bit of a preview of sort of why this works, but it doesn't just work for x squared minus 1, it works for many different possibilities. So let's do some examples here. And so what you'll be seeing for all of these is we have an x plus a number and then an x minus a number. Okay, sometimes though it's a 2x or a 5x squared, okay, but it's something plus something and then that same thing minus something else. Not minus something else, minus the same thing, okay? Let's just do them and see, okay? So foiling these guys, I'll go through the whole FOIL process here, but then for the next two, I will do my shortcut. First, x squareds, outers are minus 3x, inners are plus 3x, and lasts are minus 9, FOIL. These guys cancel, and we have an x squared minus 9. That's a difference of two squares. X squared is a square, and 9 is a perfect square also. Okay, so for all of these, what I think you're seeing is the outers and the inners from the FOIL process cancel out. So I'm going to skip those for now. Okay, so the firsts turns into 4x squareds, and the last turns into minus 25, and we're done. Okay, so we're trying to just develop a little bit of a shortcut here. The firsts turn into 25x to the 4th, and the lasts turn into 16. So we're skipping the outers and the inners, and we're done. All right, so those are two quick patterns, two quick special cases. One being up here, the perfect squares, a binomial times itself, where we had the doubled pattern and then the squared pattern. And then the next one being a difference of two squares, where we have a binomial with the sign flipped in the middle. So that plus turns into a minus, plus turns into a minus. And that results in what's called a difference of two squares. That's a good place to stop.